Hello, and welcome to Astronomy 100. In this segment, we're going to continue our discussion of the mechanics of the sky, or the appearance of movement of objects across the sky. In the previous segment, it's important to remember a term that we're going to use again, and that term was diurnal motion. Diurnal motion means daily movement, or how things appear to move over the course of a calendar day. One example of diurnal motion would be the sun. As it rises in the east, crosses the sky, and sets in the west, the movement across the sky is diurnal motion. Another example would be the moon. When it rises in the east and sets in the west, that movement across the sky is diurnal motion. So essentially everything has to have diurnal motion because it's all tied to the rotation of the Earth on its axis. As the Earth is physically turning on its axis, it creates the illusion that objects move across the sky. Now, the other thing we're going to include in this segment is by watching the sky have its appearance of movement, it can tell you something about where you are on Earth. So how you see the sky turn or how you see the sky move is partly the result of where you are relative to the North Pole or the equator of the Earth, or perhaps somewhere in the middle of the United States. So I'm going to show you some pictures to demonstrate this concept. So let's get to the first one here. Now, before we go into the in-depth of these pictures, let me first set up how these pictures were taken, because it's an important idea that you understand how these pictures were taken. Otherwise, much of this just won't make any sense. In this photograph here, what you can see is the rig that is used. This is just a standard camera, 35 millimeter, probably a digital camera, that is turned onto its back. And this is so the camera can be pointed directly up at the sky. Now, the lens at the top is what we call a wide-angle lens. Sometimes they're called fisheye lenses. And the purpose of this lens is so that you can actually photograph 180 degrees. So when this camera is turned on its back, essentially everything from one horizon to the next is recorded in the image. So when you use this camera and take a picture of what's pointing directly above your head, you will get everything in the sky, all of the horizon, and everything that's above you. Let me show you the example with this picture over here on the right. This is what we call an all-sky picture using a wide-angle lens. And what I want you to notice is if I go all the way around the circle of the perimeter of the picture, this is the entire horizon. So north, south, east, and west is swirling as I go around the horizon like this. Now, the point that is directly in the middle of this picture is the point that would be directly overhead. So the camera, imagine a line going straight up to directly overhead, that would be this point right here in this photograph. So it's really important that you understand that concept, otherwise much of this won't make sense. In this picture here on the right, there was a time component to it. In other words, they opened up the shutter and they let it stay open for probably several hours in this picture. What I want you to notice is the movement of the stars. This is what we call star trails. And the idea is that a star is normally just a pinpoint of light, but as the Earth is slowly turning on its axis, it creates the illusion that the star streaks through the picture or creates a trail. Now, I want you to notice how all the stars have trails, with one exception. This one way up here seems to be sitting all by itself, not really doing any sort of streaking or trailing. The reason is because the entire sky is turning around that one point on the sky. And the star that's right next to that one point on the sky is Polaris. If you remember from the previous segment, Polaris is very, very close to the north celestial pole. So what you're actually seeing is the result of the Earth turning on its axis. The rotation of the Earth is creating the illusion that all of these stars are swirling around that one point. So in these photographs, it will always be obvious that Polaris is where it is and the one that it is, because it's the one that doesn't seem to move. So let me show you a couple of examples of how a picture like this can tell you where you are on Earth. If you can see Polaris, you have to be in the northern hemisphere. The reason is that because Polaris is right next to the North Celestial Pole, to be able to see the North Celestial Pole anywhere in the sky, if you remember from a previous segment, then you have to be able to be in the northern hemisphere. If you were at the equator, the North Celestial Pole would be on the horizon right there. If we were at the North Pole, then the North Celestial Pole would be straight overhead and Polaris would be right here instead of right here. So this picture has to be taken from the northern hemisphere to get it to be the way that it is. The second thing is if you remember from the previous segment, Polaris is called the North Star for two important reasons. One reason is that if we take Polaris and we drop straight down to the horizon, this is the direction of true north. So if we know that this is the direction of true north, then this has to be south. Now this direction is actually east and this direction is west, because you have to remember that this is the view of the sky and everything is turned around when you point towards the sky. So traditionally this is west and this is east, but in reality, because this is flipped over, this is actually east and this is west. So north, south, east, and west, again because we're looking at the sky. So the other thing you can tell, of course, is the latitude of the observer. If you remember from the previous segment, the altitude, or how high above the horizon Polaris is equal to your latitude. So because Polaris is very, very close to the horizon here, means you must be close to the equator. If Polaris were at the center, that means it would be straight overhead, and therefore you would be at the North Pole. So this photographer was somewhere closer to the equator than the North Pole and took a picture of the entire sky. Let's look at a few other examples. This is one of my favorites. This is the same thing, camera, wide-angle lens on its back, pointed towards the sky, but this is taken very, very close to the South Pole. In fact, it's probably just a few feet away from the South Pole. Notice how all the stars seem to swirl around one point that seems rather empty. So these are all stars that are swirling, trailing through the picture because of the rotation of the Earth. And because the observer is at the South Pole, then the South Celestial Pole is directly overhead. And what I want you to notice is, whereas in the northern hemisphere we have a star conveniently close to the North Celestial Pole, that's Polaris. Notice in the southern hemisphere there is no convenient south star. So there is no single star that indicates the direction of the South Celestial Pole, but you can see that it's clearly there because it's in the middle of all this turning action. This is the Aurora Australis, what we call the Southern Lights, and this picture was taken at the research station that is at the South Pole. So it's a fantastic picture. Notice how the streaks seem to be complete circles. Well, that's because the camera was left open for 24 hours. Essentially, the entire calendar day was dark, was nighttime. And we'll find out why that is in a future segment. But you can see that the streaks complete themselves all the way around because it is a 24-hour exposure, which is just an amazing and incredibly rare photo. Well, let's compare this to the North Pole. If you were very close to the North Pole, you would see something similar. The difference is there is no research station at the North Pole that somebody was able to take a picture at. There are some places near the North Pole where research is done. So I don't have an equal picture for the North Pole, but this is a location that's very close to the North Pole. Notice how the swirling movements of the stars indicate the North Celestial Pole. It's not centered in the picture, so it's not exactly straight overhead, but it's pretty darn close. So this photograph was taken from a latitude on Earth that was high above the equator, high north to the North Pole, somewhere in the Arctic Circle, but not quite at the North Pole. So it's an amazing picture unto itself. Let's do one from the equator. If you were at the equator of the Earth, notice how the celestial poles are on the horizon. So here we still have our north, south, east, and west directions, but notice how there seems to be a pole right here. There seems to be a pole right here, and they're on the actual horizon. And now you can see the stars rising and setting, but they're still swirling. But notice how, while we're at the equator, it looks remarkably different because of our location on Earth. Remember, at the equator, the North Celestial Pole and the South Celestial Pole have to be on the horizon. And that's the only place on Earth you will get to see both simultaneously in the sky, is at the equator. And one more here. This one here is a short video that I want to show you. That is if you were at the equator and able to just turn around and look at all the different locations from different directions that you're turning, how the movement of the sky would appear. So let's take a look at this. So you're at the equator of the Earth. Notice how when we look east or west, the stars come up like this. But when we look south, you can see that they swirl over a point that's on the horizon here. This is the direction of south. And then as we continue to turn towards west, you can see that the stars again come up like this. So it's a remarkable concept of being able to see how the stars appear to move across the sky if we're standing at the equator and just simply turning in place. And this is a meteor streak that happened to be captured in the picture. This would be the direction of true north. So again, what you see in the sky is going to tell you something about where you are on Earth. Something like this would only be visible from the equator. Now let's switch to something closer to home. If we were in San Diego, we are not at the equator, we are not at the North Pole. So you'll notice in this picture here, the swirling movement indicates that there's circular movement about something that's off the picture. So one of the celestial poles is this direction, and notice the arcing trails of the stars here that indicate another pole is in this direction. So notice that the north-south celestial poles go like this. And we're not at the North Pole because this would be straight overhead, and it's clearly not. So we are still only seeing the direction of the North Celestial Pole, or that pole above the horizon. The South Celestial Pole is below the horizon. In San Diego, we're at a latitude of about 32 degrees north of the equator, and so the direction of north is, of course, still in this direction, but the North Celestial Pole is up here, and the South Celestial Pole is down here. In this photo, we are actually looking east. And the reason why is because if this is north, which means this is north over here, so North Celestial Pole, north, this has to be east, and then this has to be south. So all of these stars are rising in this picture, getting higher and higher in the sky. So this is looking in the direction of east from a latitude such as San Diego. Now one final idea is if I were to show the two of these together, what I want you to do is think for a moment. And if I were to ask you the question of which of these two pictures was taken closer to the equator, how would you answer that? So if you think about it for a second, what I want you to think about is how high above the horizon Polaris seems to be. Notice that Polaris is right here and the horizon is right here. So Polaris is very close to the horizon. Here's Polaris in this photo, much higher above the horizon. Remember, the closer you are to the equator, the closer to the horizon Polaris will be, because the altitude of Polaris is equal to your latitude. If you're at the equator, your latitude is 0, and the altitude of Polaris will be very, very close to 0, of course, if you're at the equator. So this is taken from Hawaii, which is 12 or 13 degrees north of the equator. This was taken from the foothills of Mount Kilimanjaro, which is right about on the equator. So you can see that all of this movement, North Celestial Pole, right on the horizon, all of this movement, North Celestial Pole, but a fair amount of an altitude above the horizon. And you can see in this photograph on the right, it was a fairly lengthy photo. You can see that the shutter was left open for probably 8 hours, maybe 10 hours. If this streak had gone all the way around, that would be 24 hours. If this streak had gone halfway around, that would have been 12 hours. So we're talking probably a 10-hour exposure. So it's very obvious that what you see in the sky is going to be created by the turning of the Earth on its axis. How you see what you see in the sky is determined by where on Earth you happen to be, and it's important to understand the ideas of the North Celestial Pole, South Celestial Pole, Celestial Equator, and how all three of those translate to what you see in the sky based on where you are on Earth. So these pictures are quite instructive when it comes to helping you understand how all these things come together. In the next segment, we're going to talk about the notion of timekeeping and how the movement of objects across the sky was the foundation of how we determine the passage of time. Speaking of time, we're just about out of time, so I hope you'll join me then.